So this question, we have tilted plate. On the surface, we have this liquid going through. The liquid is actually this poorly drawn, but our xy is also tilted to the plane, but the gravity is acting downward. And we can see that, and this thickness of the fluid, we're going to call it D. And if we zoom into this angle is going to be equal to theta. And this is the effect of gravity. Okay. And so this is not pressure driven, but as you can see, this is more gravity driven. Here, among rectangular coordinates and cylindrical coordinates, we know this is rectangular because we're using x and y, and this is not a pipe flow. And among them, so now we have to choose in what direction is the fluid flowing. The fluid, of course, is going to flow this way, into y direction. So among the three rectangular coordinates equation, we're going to use the one that they use Vy. So we're using this equation. And this will be y, 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 Vy. As usual, our left side is all going to be equal to 0 because it's steady state, fully developed, and one-dimensional. The right side, as we see, the velocity profile is going to look something like that. Whereas the fastest at the surface, that's meeting the air. And we're assuming that the air does not provide much shear stress or negligible amount. And we see that because it's fully developed, but the speed at here and here is not going to be different. So the Vy, velocity y, does not change, depends on the y, so this goes out. And the Vy does not change into z direction, because this is one-dimensional. So we have only one of these, because the velocity is changing whether you're on x is equal to 0 here, or at x is equal to d. So we keep this, and because this is not pressure driven, we're going to omit this as well. And we have effective gravity acting on this one, so we keep this one. And what we have resulting is this 0 on the left side with this mu times double derivative and density times gravity. We're going to move this to the left, and we have this. We take integral. Oh, before that, we're going to divide it by mu, which is viscosity. And this is what we have, and then we take integral. And before we take integral, let's look at our g. The g over here is actually, we can interpret it in terms of x. So cosine theta is equal to x over g. That makes it g is equal to x over cosine theta. So we're going to replace this g with x over cosine theta. And we take integral, this is what we have left. And we take integral one more time, and this is what we have left. And this is our velocity profile equation. Now we have to figure out what C1 and C2 are using two boundary conditions. One boundary condition is that and when x is equal to 0, the velocity is equal to 0 because it's right at the surface. And another one is at this point, at the surface, that's interfacing with the air, it will have the maximum velocity, and hence it will have derivative is equal to 0. So we have first boundary conditions, when x is equal to 0, velocity is equal to 0. And the second one, when x is equal to d, when it's facing with the air, the dv dx is equal to 0. And we have dv dx right over here. First, let's start with when apply the boundary condition of when x is equal to 0, velocity is equal to 0. Over here, if you put 0 for the place of x, 0, 0, c2 is all we have left, and that should be equal to 0. So c2 is equal to 0. And second boundary condition, dv dx when x is equal to d is equal to 0. dv dx, well, we have it right over here. Put it right back into it. So that d squared plus c1, we don't have, that should be equal to 0. Gives us c1 is equal to rho over 2 mu cosine theta d squared. Plugging, we now know c1 and c2. Plugging the c1 and c2 back into our velocity profile equation that we got earlier, we get negative rho over 6 mu cosine theta x cubed, c1, which is over here, d squared times x, and c2 is equal to 0. And we can rearrange it, and so pull this rho over 2 mu cosine theta out, negative x squared over 3 plus d squared. And that is the velocity profile of this condition.